Go ahead.
Hello. We're working on the simulation of microwave transmission lines and microwave filters. My name is Jackson Bruce, and I'm working with Demetrius Pruitt, Jalen Colt, Aaron McClinton, Christian McIntosh, and Clifford Pate. My mentor is Sashi, and I'm advised by Dr. Yang. Next slide, please. Our project goals is to learn about microwave engineering principles, to operate the AppCAD software and the Sonnet Lite software, to simulate microstrip and coplanar waveguides on the AppCAD software, to simulate microstrip and coplanar waveguide on Sonnet Lite, to design and simulate microwave bandstop filters, and to simulate a coupled lines bandpass filter. Next slide, please. Introduction. We used a microwave frequency higher than 1 gigahertz. Sometimes it can go up to 300 gigahertz for things like this, but we only went up to 3 gigahertz. We used a short wavelength less than 1 foot because we have a high dielectric constant. We're working on microwave transmission lines, and examples of those are the two on the right. The first one at the top is a coaxial cable, and the one on the bottom is a rectangular waveguide. For this, we're looking for a characteristic impedance, and that is forward voltage divided by forward current. And it's forward because sometimes the voltage and current can bounce back. The bounce back is called reflection, and in order to have zero reflection, we need impedance match. Impedance match is at 50 ohms, and it allows for maximum power transfer and zero reflection. We're also working with scattering parameters such as S11, S12, S21, and S22. And the unit for these parameters are in decibels. Next slide, please. Next slide, please. Okay. For the methodology, the first equation is the dielectric constant that I was talking about earlier, and it uses U, which is the width divided by the height, and the second and third formulas, which is A and B, to find it. The fourth formula at the bottom is the formula to find characteristic impedance, Z. And in order to find that, you use the dielectric constant from the first formula, and you use U, which is W divided by H, which is width divided by height. Next slide, please. This is a coplanar waveguide that we created on the AppCAD software. The L stands for length, the H is height, the T is thickness, W is width, and the G stands for gap between the lines. We used a dielectric of 4.6 and the FR-4, and we are simulating at 2 gigahertz. We simulated and calculated it, and we got a 50 ohms impedance, which is impedance match. So it gives us zero reflection and maximum power transfer. Next slide, please. This is our Sonnet Lite software. At the top where it says File, Edit, and all the other symbols below that bar is our main menu and our operations menu. We use that to alter, edit, and add things to the circuit. At the bottom right is our quick start guide, and we use that for our operations procedures. We follow them when creating a circuit on the software. And in the middle, where it's blank with the dots, is where we see parts of the circuit and the circuit as a whole. You can see like a model for it. Next slide, please.
My name is Demetrius Pruitt, and this is our quick demonstration video. This is a simulation of a coupled line bandpass filter. And in this window, we have a layout of a coupled line bandpass filter. It takes about 15 to 20 minutes to design and lay out on Sonnet Lite software. And we hit the analysis button to run the simulation. And in this window, we have the analysis monitor on Sonnet Lite. At the bottom, we have the frequency. Each frequency point is ran at 3 seconds. And underneath each frequency, you can see the S parameters. S11 and S21 is the main two that we focus on, which is the reflection and forward gain or insertion loss. Right now it's at 70%. And in this window, we have the graph results for the simulation of the bandpass filter. We have S11 and S21. At S21, we have a pass band at 2.5 gigahertz. Next slide, please. And this is the results from Excel. At the bottom, ER, which is the relative dielectric constant, is set at 4.4. Width is set at 1.53. Height, 0.8. We have a frequency of 1 gigahertz. Equivalent relative dielectric constant set at 3.3. And our impedance is 50 ohms. Each formula is in the previous slide presented by Jackson. Next slide, please. And these are the graph results from the microstrip impedance from the previous Excel slide. The top left, we have the line width. As that increases, our impedance decreases. The top right, as the relative dielectric constant increases, the impedance decreases. And the bottom, as our board thickness increases, our impedance increases, and all is measured in millimeters. Next slide, please.
Hey, my name is Jalen Cole. This is our microstrip on AppCAD. As you can see at the bottom, our length units was millimeters. Our frequency was 2 gigahertz. We used FR4. Our dielectric constant was 4.6. We had our width at 1.43, our height at 0.8, our thickness at 0.035, our length at 100. After we did all that, we pushed the calculate button over here, as you can see, and when we push calculate, we got a result of 50.20 ohms. Next slide, please. Here, this is our microstrip impedance from AppCAD. We had to change these numbers, as you can see, and we got these graphs from Excel. As we changed our line width, our impedance decreased. As we increased our thickness, our impedance increased. As we increased our relative dielectric constant, impedance also decreased. Next slide, please. Here's our results from coplanar waveguide on AppCAD. We had we kept our lengths at millimeters. We used that a lot. We also kept our frequency at 2 gigahertz. We also tested to see what it would do at 1, and it wasn't much of a difference. We still kept FR4. We kept our dielectric constant at 4.6. We kept the height at 0.8, the length at 100 or 1,000. 1,000, that would not affect the impedance. We kept the width, we changed the width to 1.25. The gap, which is in between, we put that at 0.53, and we kept the thickness at 0.035. We pushed without ground plane and calculated, hit the calculate button, and as you can see, we got 50 ohms, which is characteristic impedance. Next slide, please. Here's our results that we also got from Excel of our coplanar waveguide impedance from AppCAD. Our line width, as we increased our line width, impedance decreased. As we increased our board thickness, impedance increased. As we increased our gap, impedance increased. As we increased our line thickness, impedance slightly took a decrease. Next slide, please. Here's our 3D microstrip on Sonnet Lite. As you can see, we have port 1 and port 2 on the left and right. Port 1 is input, port 2 is output. The pink line in the middle, as you can see, is our transition line, which is 50 ohms. The gray part that you see on the bottom that is shaded gray, that part is grounded. The rectangular part that you see on top of that is the metal box that covers our circuit board, and all the calculations are within this metal box that's covering that microstrip. You can't see the subscript part of the microstrip from this view on the bottom. You can't see it. Next slide, please. Here's our microstrip simulation results from Sonnet Lite from that previous slide you just saw. We have the blue line, which is our S11, which is the reflection line. That is, it starts at about -40 decibels. As you can see at the bottom, we have our frequency, and it's from 1 to 10. And as you can see, our reflection where it changes during those frequencies, the gigahertz. At the top, that is the pink line. It is S21, which is almost at 0 dB, which means that it's almost 100 pass rate, which is almost at 50 ohms, which is characteristic impedance. Also, about this -40, that is 10 to the -4, or 1/10 to the -4. Next slide, please.
All right, hello everyone. My name is Aaron McClinton. So here we have our coplanar waveguide on our Sonnet Lite software. As you can see, we have, this is a 2D view, by the way, of our coplanar waveguide. As you can see, we have our transmission lines in the middle. We have our port 1 on the left, which is our input port, and we have our port 2 on the right, which is our output port. And as you can see, we have different measurements in between these transmission lines and the rest of the coplanar waveguide. So that helps us out in determining, how far they are apart from each other. And we have our quick start guide in the middle, which basically lists the procedures for simulation on this coplanar waveguide. Next slide, please. So here we have the 3D view of our coplanar waveguide on Sonnet Lite. As you can see, the top is pink, so it's not grounded. We still have our ports on this one, as you've seen before in the 2D view, but this is just our 3D view. So we still have our port 1 on the left and our port 2 on the right, input and output ports. We still have that box, as Jalen mentioned, around the around our coplanar waveguide. And the bottom of it is shaded gray, which means it's grounded, accompanied by the transmission lines in the middle. So next slide, please. So here we have our coplanar waveguide simulation results from Sonnet Lite. So also, as Jalen stated before, we have our S11, which is our blue line, which is our reflection line. And we still have our S21 at the top, which is still our transition line, which is in pink. And on this simulation, our reflection, our S11, it started at about -35 decibels. We're still measuring that in decibels, and we still have our frequency on the gigahertz at the bottom across. But our it measured about -35 decibels, our reflection line, and it continued to go down to about -68 decibels, around 2.1, 2.2 gigahertz, and go around and stay constant at -35 decibels. And at the top, our transition line, it stayed at 0 once again, which means that it's 100 pass. So yeah, basically our transition line still stayed at 0. Next slide, please. All right, so here are our results for our open stub bandstop filter. So based on our calculations from week 2, our design of the bandstop filter had a center frequency of 2.0 gigahertz. Our line width turned out to be 1.52 millimeters. Our impedance is 50.25 ohms. Our wavelength is 21 millimeters, and our quarter of a wavelength is 20.55 millimeters. And as you can see, most of our lengths and widths are measured in millimeters. As you kind of can see it before on the AppCAD also. And at the bottom, we have our Excel file, which has all of these calculations on it. As you can see, next slide, please. All right, so here we have our first order bandstop filter layout in 2D. As you can see, we have our quarter of the wavelength, which was at 20.55. As you can see, the measurement at the top line, and then we still have our input and output ports, port 1 and port 2, on the left and right. And as you can see, our line width in millimeters is highlighted on the bottom line. So next slide, please.
Hello, my name is Christian McIntosh, and here we have our first order bandstop filter simulation results. We have our 2 lines, which is our blue and pink line, which making the blue line our S11, which is our reflecting coefficient, and our pink line is our S21, which is our transmittance. As you can see, we have a 2. As you can see that our transmittance create a frequency of 2 with a magnitude of minus 30 dB. Next slide, please. Here we have our second order bandstop filter layout. We have our 2 open stops in the middle. They both are a quarter of a wavelength apart. At the bottom, we have our transmitter with our input 1 on the left and our output 2 on the right. Next slide, please. Here we have our second order bandstop simulation results. As you can see that our S21 creates a frequency of 2 gigahertz, and it creates a stop band with a continuation depth of minus 50 dB. Next slide, please. Okay, here we have our fabricated second order bandstop filter. Like the first image, it's just a real image. We have our 2 open stops. Both are still a quarter of a wavelength apart. And at the bottom, we have our input 1 on the left and our output 2 on the right. Next slide, please. Okay, here we have our second order bandstop filter measurement results. As you can see, our S21 has a stop band of 2 gigahertz of frequency and a continuation depth of minus 50 dB. Next slide, please. And here are the simulated and measured results on our second order bandstop filter. We have our measured results and simulation results. Both have a frequency of 2 gigahertz and a magnitude of minus 50 dB. Next slide, please.
My name is Clifford Payne. I'm the RIT teacher for the Alabama A&M group, working on the microwave transmission lines. So the last device that we built was a coupled line bandpass filter. Previous couple of items were bandstop filters that were stopping certain frequencies. This is a filter that's going to pass through a certain frequency. It's kind of similar as a input 1 on the left, output 2 on the right, but instead of a transmission line that runs straight across, it has those 4 parallel sections in the middle. This one is the one you also saw in the video demonstration. So it takes a little bit longer to build, about 15 or 20 minutes, to be very precise with the Sonnet Lite software. But we're going to look at the results on the next screen. So next slide. So again, this was the output that you saw from the analysis. So after we analyze the circuit and run that through, we see all the different frequencies from 1 to 4 on this particular graph. What you notice is kind of a reverse of what we saw before. This one, the pink line, which is the transmittance, the S21, this one has a peak at about 2.5 gigahertz. So basically everything to the left of 2.5 is being blocked, everything to the right of 2.5 is being blocked. This device is allowing those 2.5, that 2.5 frequency to pass through. That's why you see the reflection is lower at that point, and you see the pass at 2.5. Next slide, please. Okay, so to summarize everything for the undergraduates and myself, first of all, for the undergraduates, they learned all of the microwave engineering principles, went back and reviewed everything they knew about that. They learned how to operate the two softwares, the AppCAD and the Sonnet Lite. They use the formulas to go through and calculate what the microstrip impedance should be. So you saw that on the Excel file. So on the Excel file, they would go through and try different widths and heights and thicknesses until they were able to get that 50 ohm impedance, which is the industry standard that they want. So once they were able to get those measurements of what those should have been in order to get 50 ohms, they would go into the AppCAD software and simulate the microstrip and the coplanar waveguides on the AppCAD. The AppCAD would verify that those devices with those measurements would give them the 50 ohms. Once that was done, then they took those measurements and went into Sonnet Lite and simulated the actual devices themselves. So once those are simulated, they can analyze at all the different frequencies to see what happens at each of the individual frequencies. That's where we saw that for certain frequencies, we would get that full pass and everything there. On my side, for the teacher side, I have a teacher class called Mathematical Modeling. And so in that class, I've never really had a way to connect some of the stuff we did in there with statements and true-false statements. But I did go back and I found some problems that had to do with circuits. So on the bottom right, you see kind of a parallel/series circuit where the question would be, whether the light bulb is on or off, which is a really simple problem if you think about it. But in terms of connecting it to these circuits, an open circuit would be where P, for example, there at the top is open. Well, that would map to a false statement. Where if that circuit was closed, if the switch P was closed and the light bulb would turn on, that would be a true statement. And so since my kids also, we have what's called a computer science strand in my school, like programming classes like Java and Python. With a class like that, the kids can take those logical statements for circuits and kind of build that into their programming language. So if this is happening, then this will happen. And if this circuit is open, this will happen, or if this circuit is closed. So we're going to go back and try to rebuild some of that when I teach those if-then statements this year and the logic stuff, and connect that to how that would work in these circuits. And then to extend on that for the smart city applications, I envision that being something like when a certain device gets near a network. So if your smartphone gets near your Wi-Fi network, then it might turn on your lights or it might open your garage door. So that would be some kind of smart applications that circuits would connect to. Here at the Space and Rocket Center, they do an app and a coding contest where the kids can write apps. So that's something the kids could apply that to some of the contests that they enter. And then even into the 5th generation wireless networks that are out there. So 5G is becoming the new standard for smart devices. And we'll talk about how those apply to these wireless networks and how these transmission lines and filters are built into those new networks and what that means as far as the higher transmission speeds, the lower latency, so there's less delay in how those devices work. Next slide. Okay, we were also going to author a little paper for a journal because both of the softwares we used were free, the AppCAD and the Sonnet Lite. So for designing these circuits and simulating these circuits, very beneficial for our undergraduates to be able to go to an employer in an interview and say that they were familiar with using these free softwares, which are pretty exciting for them to have that experience. I work on a paper for a journal for that. And our last slide is our references. And so the first two references there, microwave engineering and microstrip filters for RF, are basically the textbooks where we found all of our formulas and all of our calculations that we needed. The third link there was how we use the analyzer. That's just the user guide for the analyzer. So once we simulated these results, you saw that we wanted to match that to what the device would actually measure in the real world with our real device there. I think it's going to be the second order filter there, the real one. The next two links there are just the links to the free software that anybody can download. So Broadcom and Sonnet software, the AppCAD and Sonnet Lite. And the last link there is just the user guide and tutorial, video tutorials for how to build those circuits in Sonnet Lite. So you can design those circuits and